Can we start now?
Yes, Patrick,
Yes.
please go ahead.
Okay. So good morning, good afternoon, or good evening, everybody, and thank you for joining us for this webinar on reducing greenhouse gas emissions from fertilizer use. I will be your moderator today. My name is Patrick Effer. I am the Deputy Director General of the International Fertilizer Association. It is my pleasure to introduce Dr. Emba, who will present opening remarks on behalf of FAO. Dr. Emba is Deputy Director of the FAO Plant Production and Protection Division. In this capacity, he provides strategic and thought leadership for the extensive global portfolio of normative and operational interventions that assist FAO's member states to achieve the Sustainable Development Goals through the transition to more efficient, resilient, and inclusive crop production systems. So with this, over to you, Dr. Emba.
Thank you so very much, Patrick. I think Chike will just do fine as the name. Anyway, distinguished guests and participants, dear friends and colleagues, ladies and gentlemen, good day, everyone. It is a distinct honor and pleasure for me to address you today as we assemble for the fifth in the series of seminars that are jointly organized by the Food and Agriculture Organization of the United Nations, that is FAO, and the International Fertilizer Association, IFA. Today's session is ever so aptly titled Reducing Greenhouse Gas Emissions from Fertilizer Use. Yes, this title is apt, both because the theme is unquestionably germane to the sustainability in development discourse, but also because the timing of this event is opportune. This is because we at FAO are planning our work for the next 2 years, and so can use any meaningful insights that enable evidence-based visioning. The timing is also right because COP28 summit has just ended with a renewed commitment to the reduction of greenhouse gas emissions. Granted, the emphasis of the so-called Global Stocktake Agreement that was reached yesterday in Dubai is on fossil fuels. However, I will say that any metric ton of carbon dioxide equivalent, irrespective of the source, is one too many. But ladies and gentlemen, let me take a step back first. To set the scene, as Patrick said, I will situate this event within the overarching context of the work that we do at FAO with you all partners. Sadly, hunger continues to increase globally. Last year, 1 in 10 persons globally bore the unconscionable scourge of hunger and malnutrition. In sub-Saharan Africa, the statistics were even more dire, with almost a quarter of the population being food insecure last year. My dear friends and colleagues, that is almost 1 out of every 4 persons in that sub-region. And as we all are aware, climate change, strife, and other drivers confound efforts to produce the significantly more food that is needed to nourish everyone on planet Earth adequately. But all this notwithstanding, FAO's leadership is resolute that the Sustainable Development Goals, SDGs as we call them, especially SDG 2 on zero hunger, is achievable. The FAO Strategic Framework 2022 to 31, with which the organization seeks to transform agri-food systems to become more efficient, inclusive, resilient, and sustainable for better production, better nutrition, a better environment, and a better life, leaving no one behind, is lesser focused on achieving these sustainable development goals. That is why, dear friends, I say that our work is cut out for us in the Plant Production and Protection Division, as more than 80% of all food is plant-based. In rising to this challenge that faces all, we have adopted the mantra of optimization and minimization. That is, optimize the positive aspects of crop production systems, such as productivity, yield, and nutritional qualities, and minimize all the negative aspects, such as the deleterious environmental footprints of production systems and the negative impacts that they exert on human health, the environment, and biodiversity, such as those caused by the overuse of fertilizers, which we shall soon hear contributes to climate change inducing greenhouse gas emissions. So, ladies and gentlemen, on one hand, more food must be produced, but on the other, this will not be at the expense of the environment or indeed of our health. In fact, 50% more food than was produced in 2012 must be available for the adequate nourishment of everyone by the middle of this century. To achieve this significant increase, fertilizers must be used. Yes, farmers must use fertilizers. The question before us rather is, how can we use fertilizers to boost crop production significantly without contributing to climate change or indeed further damage the environment or pollute our water? This is why, ladies and gentlemen, I salute the sagacity of the organizers of this webinar, both at FAO and at IFA, for assembling this august set of thought leaders to share perspectives and insights on how the imperative of producing more with less may be achieved. Dear friends and colleagues, ladies and gentlemen, I anticipate that this webinar will yield valuable insights on actionable means for the reduction of greenhouse gas emissions from fertilizer use in crop production systems. I am that optimistic. And I urge every one of us, therefore, to engage actively and share insights so that this will be a worthwhile experience for us all. And with that, I sit back. I invite you all to also sit back while thanking you all so very much.
Thank you very much, Chike, for these very inspirational opening remarks. And so maybe just before I continue, I would like to say a few words about IFA because not everybody knows what we are. So we are the International Fertilizer Association, which is a global body representing plant nutrition solutions providers. So that's not only the mineral fertilizer producers. We have almost 500 let's say members in 80 countries. And our mission is to help feed the world. When it comes to climate change, it is, let's say, our objective is to decarbonize both fertilizer production and fertilizer use. And the focus of our webinar today is on the fertilizer use component. So I'm glad now to see that we have already almost 190 people online, which is great. You can see here, many people are already using the Slido function. I encourage you to join it. Just scan the QR code here. and to respond to the question. So you have seen the word cloud at the beginning, showing a huge diversity of people in terms of geographic origin, also in terms of sectors represented. We will use a Slido function as well during the webinar in case you would like to ask questions to presenters. So as mentioned by Dr. Emba, so mineral fertilizers are essential to boost agricultural yield, also feed a growing population, and at the same time mitigate pressure for land use changes. At the same time, mineral fertilizers, especially nitrogen fertilizers, when it comes to their use is associated with greenhouse gas emissions of about 700 million tons of carbon dioxide equivalent, which is about 1.5% of global greenhouse gas emissions. And we need really to address these emissions if we want to achieve the Paris Agreement objective of 1.5 degrees. While low-emission solutions exist, they need to be widely adopted across farming systems to make it happen at scale. And that's really the objective today, how to make it happen at scale. Our webinar today will look at the potential of existing solutions and what policy and or market incentives and innovations are needed to accelerate adoption. So today we have 4 distinguished speakers who will update us on greenhouse gas emissions from agriculture and fertilizer use in order to set the scene. We will have also a presentation on the reduction potential and the main interventions to reduce emissions from fertilizer use. Then one of the presenters will explain the role of the fertilizer industry to help farmers reduce nitrous oxide emission and sequester carbon in soils. And finally, the last presenter will elaborate on the role of policy to reduce emissions from fertilizer use. So each speaker will be given about 15 minutes for his presentation, and we will then have a moderated Q&A part. And please, during the presentation, if you have questions, use the Slido function, ask your questions, and then the moderator of the panel discussion will ask questions to the speakers. So with this, it is my pleasure to welcome the first speaker, Francesco Tubiero, who heads the Environmental Statistics department at FAO, where he developed the FAO Stat Agri-Food Systems Emission Database. Francesco is the lead author of several IPCC reports investigating the linkages between climate change, agriculture, and food security. And he was recently recognized by Reuters among the world's 200 most influential climate change scientists. With this, Francesco is going to update us on greenhouse gas emissions from agriculture and fertilizer use. So over to you, Francesco.
Thank you, Patrick, for the nice introduction, and good day to everyone, wherever you are following this webinar. Thank you, of course, for the invitation to present our work. I will share my screen right away, and please let me know when you see it.
Yes, we can see it.
Excellent.
You can put it in
yes.
Full screen. Yes, perfect.
Okay, so I'm honored to begin this technical part of our discussions, providing, as Patrick said, an overview of greenhouse gas emissions from agriculture, and we'll use this to set the stage and put the more focused discussion on fertilizer in focus. In fact, if you allow me to expand the view from merely, quote unquote, agriculture to the way we look at things recently, both around the world and certainly at FAO, which is in terms of agri-food systems, whereby agri-food systems, as you see in the slide, we intend the full continuum from the activities that happen on the farm for crop and livestock production, to the impacts on the surrounding ecosystems, especially linked to expanding agricultural land, linked to processes such as deforestation and other degradation of natural ecosystems, and extending that to both the supply chain of whatever happens to our commodities once they leave the farm gate, transport, the processing, the retail, the household consumptions, and the waste disposal, as well as some of what we call pre-production processes, which are germane to this presentation, because they also include emissions from the production of inputs. So this is, in a nutshell, the way we like to look at this, and that we have proposed from within FAO to look at these three pillars of farm gate, land use change, and pre and post production. And so I will walk you through what is the overview of emissions that come from these processes. But before going forward, for those of you who are also, since we have mentioned the COP and the climate processes, they've just concluded in Dubai, to provide also a parallel view of all of these processes from the point of view of climate policy. And when it comes to emission, the key word here is national greenhouse gas inventories. And those that will talk about mitigation will certainly touch upon this. But just to put forward this idea of different worldviews, right? So there is a view that people that are engaged in agriculture professionally recognize very directly, and another worldview that people that write inventories and communicate to the Climate Convention recognize more directly. And often there is a lot of details lost in translation between these two ways of looking at the world. And so one of the things that we also do in FAO is providing the linkages so that various actors that play in many important roles in these processes can understand each other and be more effective in the actions that they are proposing. Now, let's get very directly to the global highlights. So what do we know about emissions from agri-food systems in the most general way to look at them? And many of you might have written recent papers which have highlighted that once you compute and translate all the emissions in CO2 equivalents, those emissions are about 30% or a third of all the emissions that we emit from human activities. And that alone is used as a rationale for including actions in agriculture, but across the value chain, to contribute to the commitments that countries have made and with the Paris agreements to reduce those emissions as quickly as possible. So if we want to talk about numbers, I come from a statistics division. So what we do in terms of service to our colleagues is put out numbers that could be useful. So we're talking about 16 billion tons of CO2 equivalent in 2021, over a total of about 55 emitted from all sectors, right? So this corresponds to about 30%. You will see also that over time, this share has been decreasing. It was as high as 40% 20 years ago. And the reason for that is mainly that the sector, in terms of emission, because it's only a share of energy use, has been growing a lot less than the rest of the fossil fuel energy sector. The other important message or piece of information to carry with you here in the context as you go down towards fertilizers is that these emissions are sort of dominated, again, by emissions on the farm, what IPCC calls properly agriculture, by considering, generally the non-CO2 emissions, so the methane and the N2O, which will so important for fertilizers, and also a little bit of CO2 from mechanizations on the farm. And the rest comes with an increasingly diminishing share from the land use change processes such as deforestation, which, although reassuringly have been diminishing significantly over time, they still represent several billion tons of CO2 gas emitted into the atmosphere. The other thing to, to keep in mind is that the latest piece of information that we've added over the last 2-3 years to this picture, which is the pre and post, but let's call it the supply chain emissions, those are actually quite important, and they are becoming, well, they are certainly the fastest growing sector of agri-food system emissions historically, and they've become, in many countries, in many parts of the world, as we will see, even the dominant component of those total emissions. Couple of things to highlight when we go from global to trying to look at some sort of regional characterization of these emissions. So what you see here is 2 sets of bars. To the left, you have emissions from OECD, developed countries. If you will, if you are in the climate convention world, these are typically the so-called the Annex 1 countries of the convention, parties to the convention. And on the right, you see the emissions from developing countries. Now, of course, the relative difference in absolute amounts also has to do with sheer area and number of people and number of animals and agricultural area that makes that difference. So that's explainable. But when you start looking at indicators that reveal the structure of these emissions, you start seeing very interesting things. First is that the share of agri-food system emissions in developed countries is around the world average, let's say around 30%. But it's been increasing over time, over the last 30 years. Now, the opposite is true of countries that are developing, and partly if you look at this angle from a perspective of agriculture, these are countries where there is increasingly a shift from traditional to intensive agriculture, and where, of course, agriculture dominates the economy, the overall economy. So the share of those emissions to the total is much larger. It was actually 60% 30 years ago, and it's about 40% today. So the trend in those shares is actually opposite, and it goes hand in hand with the economic development story that I just provided. The other very interesting, at least for me, and I hope to interest you with this storyline, also stimulating the discussion, is the difference in the relative shares of the relative contributions of the 3 pillars in the 2 group of countries. So in developed countries, as I mentioned before, emissions from the supply chain have actually become the dominant part of the emissions, and this is very easily understood, exposed, if you think about the development of the supermarket, of the verticalization of food, on everything that we see in our cities, bring us to use more and more energy to put to fruition the food that is produced, and of course linked to energy use, to F-gases, to all the let's say modern means of greenhouse gas emissions that we are familiar with. Contrast to that, in developing countries, of course, emissions on the farm are important, but there is an important component of emissions that comes from land use change, because farms in that part of the world are also actively expanding to meet increased need for food production and supply and demand. Also, quite interestingly though, you also see a similar trend in terms of the emissions from the supply chains. These have been growing very significantly, and so are becoming an important component of the agri-food system emissions that need to be addressed in terms of mitigation. Now, that was the sort of the global, sort of very high level regionalized picture that it's important to keep in mind when we start then to focus more on emissions from fertilizers. So what is the fertilizers emission angle in all of this story? And here, from a little vignette that I had shown in the beginning of my presentation, I highlight the 2 components where these emissions are important. There is emission, like Patrick said, that happen on the farm, okay? And these are linked to fertilizer, and in fact, they are linked both to mineral fertilizer and importantly also to the application of manure. So the two processes combined contribute to a significant amount of emissions, as we will see soon. Then, of course, there is the manufacturing of fertilizers needed for that production that also contributes important components of emissions. And of course, the two processes delineate, let's say, the mitigation space that is possible, that it needs to be considered when we talk about mitigation options. Couple of last slides, again, to put things in perspective and then close for the next presentations. You've seen before that I have mentioned that emissions from agri-food systems constitute about 30% of the total, right? And the relative components of the three pillars that which you see here replicated in terms of numbering, of coloring labels, right? Again, the yellow is the farm, the green is what happens on land, and the blue is the supply chains. Of course, so when we talk about mitigation, and this is sort of the power of the kind of databases that we put out, and this is, by the way, is the global picture, but in FAO-Stat you could look and replicate this very picture for every country in the world, for every region, for every development economic group. So you see that there is a vast array of processes that emit from farm to consume, okay, as we all know. And these are dominated by things that are not necessarily, or at least they're not directly related to fertilizers. And the main thing to highlight in this picture is, of course, the role that, on the one hand, livestock, but in particular ruminant livestock, plays in terms of methane emission, and of course the other role of sort of just adjacent to the farm of the of the deforestation and ecosystem degradation that play a fundamental role. You see, and I'm not pointing yet to fertilizer because I will in a second, that fertilizers and manure play important roles as long as they're put in the right context of the rest of the contribution from all other processes. Now, the other thing that needs to be considered here is that different processes emit different greenhouse gases. So you see here the CO2 and the N2O and the methane associated to different processes. So there are two angles to mitigation. One is, the overall goal of staying within 2, possibly 1.5 degrees, which is, as was said before, is addressed by anything that we can do across the board of all the emissions that we put out in the atmosphere. On the other hand, there is a different way to look at this, which is, what processes contribute to different gases. So if you only look at N2O, which is a very important greenhouse gas, as important as CO2, because it does stay in the atmosphere hundreds, between 100 and 200 years before it gets degraded, and it's a powerful greenhouse gas. It is 200 to 300 times more potent ton per ton than CO2. You then see that the picture becomes more relevant when you try to identify the role of fertilizers in this set, right? So when you look at the 30%, fertilizer play a minor role, but if you look at the N2O, they become quite important. Important because within this makeup of processes, they basically dominate. And important because, and this is the last point, or second to last point I wanted to make, if you look at that share in terms of CO2 equivalent, agri-food systems to total human emissions, we return to the 30% that I mentioned in the beginning. The picture changes gas by gas, and you see that when you look at N2O, basically the entire story comes from within agri-food systems. About 80% of those emissions come from this system. And of course, fertilizer now play a fundamental role within that important picture. I leave you with a storyline, if you will, or a different way of looking at these emissions from a perspective of indicators. In this case, we're looking at emissions per unit of value of production, right? At the end of the day, when we think about solutions on the farm, they make sense both for greenhouse gases and for efficient production of food and provision of food. The bottom line will be the economic performance and the efficiency of that economic performance of farms in a country. So what you see here is the top 10 countries in terms of absolute value of economic production in the world, and you recognize the list of countries here. So it's not a top 10 list, it's the top 10 in terms of value of production. But then what you see here is it's associated greenhouse gas efficiency, if you will, right? So how many greenhouse gases, kilograms of CO2 equivalents are emitted per dollar of value produced on those farms. And this is a different presentation, so I won't get into the details. I just wanted to highlight two things. One is countries where this efficiency is worse are obviously countries that have not only emissions produced on the farm, but also emissions that are produced on the surrounding of those farms, deforestation, degradation of tropical peatlands, especially in Brazil and Indonesia here highlighted, which are countries where those processes happen and are well documented. But the other thing to notice in this graph is that in those same countries, even if you were to take the green bars, parts of those bars out, the efficiency would still be pretty low compared to others. And actually, there is a connection with the two things, right? The reason why those countries need to have farming expanding outside is because they don't have very efficient production to begin with, right? So more food can only be achieved in part by expanding with more agricultural land. And I think in there lies, a storyline for linking nitrogen use efficiency of production with all the other processes that we want to address moving forward in the next decades. So with that, I thank you. Patrick, over to you.
Thank you very much, Francesco, for a very informative presentation. And so I remind all the speakers, please stick to 15 minutes, otherwise we won't have much time for Q&A at the end. So now let me welcome our second presenter, that's Floor van Dam. Floor works in the Amsterdam office of Systemic Systems Change Company, where she focuses on the interplay between the nature positive and energy transition. Floor has advised governments and the private sector on industry decarbonization pathways, focusing on green hydrogen and ammonia production. She has been closely involved in the systemic publication, Reducing Emissions from Fertilizer Use, that was commissioned by the International Fertilizer Association. So Floor is going to present a general overview on practices reducing emissions from fertilizer use and their potential. Over to you, Floor.
Great, thank you very much. Can everyone hear me and see the presentation I'm sharing? Great, I see people nodding.
Yes, absolutely.
So before we kick off, on slide A, if all is well, there is another question, but the question is actually, by how much can we reduce fertilizer-based emissions? So is that by less than a third, between 1/3 and 2/3, or by more than 2/3? And I wanted to start with this question, just kind of, open everyone's mind and think through what's the starting point here? What is the potential? So whilst I give everyone maybe some time to think about this question. And then already some answers. Okay, so I think majority, or it's tight, but almost 44% says more than 2/3, and 44% says between 1/3 and 2/3. And that's exactly what we want to talk to you about today. So maybe a brief introduction. As Patrick already highlighted, I work at Systemic, which is known as a systems change company, where we focus on transforming the systems at hand to kind of align with the Paris Agreement goals. And within that, we do advisory work or more coalition work, or we help with thought pieces. One of the thought pieces we did was a combination of the nature and energy system is looking at reducing emissions from fertilizer use. And we made a model there, and according to our model, greenhouse gas emissions from mineral and nitrogen fertilizers can actually be reduced by around 70% by 2050. There's, of course, a big but there as well, right? Because this is only possible if specific actions are undertaken. And some of these things are still extremely challenging. So there's a lot needed to actually reach this target. And that's what I want to talk about today. So in short, in the next 15 minutes, I will be focusing on briefly highlighting the current state of play, building on what Francesco has already been talking about, then highlighting the need for collaboration throughout the value chain, then touching upon some key interventions to actually decrease these emissions. So I already saw some questions in the Q&A, and I hope to touch upon some of these questions. And then also zooming out and looking through, okay, what actions can we then actually take to embed these interventions? Now, going through the current state of play, Francesco's already touched upon a lot of this, right? But I think key here is to highlight that mineral fertilizer, it's not a joke. Global emissions from mineral fertilizer use are roughly the same size as the total emissions of Germany. Maybe a different example is that it's almost equal to the aviation sector, emissions related to that. And then comparing how much we talk about aviation and how much we talk about fertilizer use, I think there's still something to win. It's maybe not the most sexy topic, but it's nevertheless very important. And what you see in this graph is, again, these total greenhouse gas emissions. It was highlighted that this 30% of total comes from agri-food, then translating that to the farm gate emissions, and then after that translating the farm gate emissions and looking at the different sectors and the impact of mineral fertilizer. Big note here is that Manjura is also part of it, but our scope currently or for this day is mineral fertilizer. So from this state of play and this conclusion that mineral fertilizer, it has a big role to play, it's good to then zoom in, and I think Francesco also touched upon this, about where these emissions come from. And the key element of the overview that we show here is that fertilizer use is actually 50 to 80% of the total emissions associated with the fertilizer production, the energy you need to produce it, the natural gas, and then transport emissions from the upstream side. So it's quite a critical element of it. And the major sources of variation of why it's 50 to 80% are related to the application rate, the method and timing, so the soil and climatic conditions, and the crop type and rotations. So zooming out here, collaboration is quite key to touch upon these kind of scope 3 and scope 1 and 2 emissions. Now, from the current state of play, so we've rushed through that, so there is a problem. There are quite significant emissions we're talking about. Then towards, okay, there's collaboration needed because we're talking about the scope 1, scope 2, scope 3 emissions. We would now like to focus on the key interventions to actually decrease these emissions. And we'd like to touch upon 3 different, let's say, buckets to say. So the first one I'd like to focus on is improving nitrogen use efficiency, then the increased use of inhibitors, and lastly, the wider food system changes. Now, when we talk about improving nitrogen use efficiency, what we actually touch upon is the 4 R's. So are you applying fertilizer with the right source that actually matches the crop need, the right rate, so that it's actually the right amount of fertilizer and it doesn't really leach into the area surrounding it, the right timing, so when actually a crop needs fertilizer, and the right place. And by improving this nitrogen use efficiency through enhanced kind of management practices, but also this efficiency, and really eliminating inefficient fertilizer use, there's quite a big role to win there. From this pillar 1, we focus on the second pillar, which is an increased use of inhibitors. So in general, inhibitors are compounds that are added to a nitrogen-based fertilizer that restrict the production of greenhouse gases and nutrient leaching. So they slow the conversion of nitrogen fertilizer to other nitrogen compounds that would then leach into the soil. And the focus here is on nitrification inhibitors, which can help to reduce direct emissions, urease inhibitors, which can help to reduce the indirect emissions through volatilization. And it's quite critical that looking at these different inhibitors, that really a lot more research is needed to really understand these products' wider environmental impacts. For example, also looking at the impact of microplastics in a way. So there's still an element of research needed to really engage with this on a large scale, but it is a big pillar and a big role that it could play in our research. And then lastly, there's the pillar of the wider food system changes. So what we focus on there is the increased cultivation of nitrogen-fixing crops, so we have the crop rotations, also possibly a shift in consumer behavior towards these crops that are have this impact. And then also further looking into a dietary shifts towards more plant protein. So away from these animal products, which would also reduce the mineral nitrogen fertilizer requirements. Now, these three buckets, they're nice. So we're looking at NUE, increased use of inhibitors, and wider food system changes. But the key question now is how that translates into the potential. And that's what you see over here. I think the key conclusion of this slide I'm showing is that Scope 3 emissions from the use of fertilizer can actually be more than halved by 2050, mostly under influence of the sector itself. So if we go from left to right, what you see here is that in 2020, we have 715 megaton CO2 equivalent per year emissions. To 2050, if there's no productivity growth, this is going to be growing. And then we take a business as usual productivity growth, because we do expect that already steps will be taken. And after these, the green and the yellow column come the three topics we've been discussing. So the first one is the potential of NUE best practices. And what you see there is that actually quite a large chunk can be reduced because of these practices. The next one is then this increased use of inhibitors. So you see about 20%, which can really have this impact of reducing emissions. And then lastly, you have the impact of crop rotations and land sparing. And what we did here is, this is quite a global story, what you see here. And in our modeling, what we then did is we also really took a regional approach. And why this is, I think Francesca also highlighted this, and it's again two big graphs, but on the left hand you see the different regionality of the greenhouse gas emissions. But I'd mostly like to focus on the right side here, where you can actually see the different regions and the global nitrogen thresholds, which have been exceeded in different regions. And basically the key takeaway from this, what we're showing here, is that its regional approaches are critical, because what works in a certain region does not work in another one. And that's also what you see here in kind of we looked at 6 different regions and their kind of the case studies there. And that's also what we saw, is that not every region needs the same solution. So inhibitors could work in US, Brazil, or China in the rice system, but would have a bit less impact in Europe in the wheat food system. So rushing through this one, because it just kind of shows, okay, the regional differences are key, I would like to mostly focus on the next slide, where we show for these 6 different regional deep dives what the marginal abatement cost curve looks like. And I think there was also a question in the chat where I think it was asked what economically would be logical. And what you see here is that around a quarter of the measures identified in these regional deep dives are actually cost saving for farmers. So to the left, you see that for China, US, France, mostly the NUE, so the nitrogen use efficiency measures, are cost saving. And then inhibitors and crop rotations might actually have a significantly higher cost abatement cost. And so within our research, we kind of come to the element of, okay, there's a regional element to it, but there is really this side that there are economical wins as well, because you are saving the use of fertilizer. So we've now gone through the current state of play, how much emissions, and then the key interventions. And what I'd like to close with, if that's still possible within the time, I think it is actually zooming back in. So what are actually the key actions to take? And I think it's quite powerful that we're here. I heard 190 people, so I think we can actually take some actions together. And within that, I think collaboration is quite key. And what we're trying to show here is that if you're a fertilizer company, or if you're representing a fertilizer company, your scope 1 and 2 emissions are a farmer's upstream scope 3 emissions and a food manufacturer's upstream scope 3 emissions as well. So there's an incentive there to collaborate. The same holds for farmers. So a farmer's scope 1 and 2 emissions are the fertilizers company's downstream scope 3 emissions, and a food manufacturer's upstream scope 3 emissions. So there's also incentive to collaborate on this topic there. And lastly, if you're a food manufacturer currently listening into this webinar, your scope 1 and 2 emissions are equal to the downstream scope 3 emissions of a farmer. So there is really, these emissions are actually of interest to the wider food system. It's not just a you problem. And that's why I would like to end with this slide, where we show what companies can do through 3 different segments. First of all, it starts with looking at yourself. What individual action can you take? Then it's all about collaborating with others in the sector. And lastly, it's about partnering with downstream players in the value chain. So looking at these 3 different pillars, is lightly touching upon them, and you can find more in our study we did as well, is when it comes to taking individual action, it's really about figuring out what the availability is of the right project. So which tailored products, which nutrient blends can you actually use to ensure that there's less nitrogen emissions. Then it's all about educating and incentivizing advisors. So changing the incentive structures. So the incentive is not to, for example, sell as much fertilizer as possible, but to potentially sell a service of crop growth. And lastly, there's an element of addressing these technical barriers. As I highlighted, for example, about inhibitors, really some research is still needed to use this at a wide scale. So it's really about increasing R&D, the in-house, both in-house, but also pre-competitive collaboration. Looking at collaboration with others in the sector, it's all about this sector-wide collaboration on outreach. Together, you can actually collectively fund a larger farmer outreach activity to promote emissions reduction. Together, you can also really push standard setters and certifiers, unlocking a higher value for farmers. And lastly, together, you can actually really advocate for policy reform, creating a perverse incentive for inefficient fertilizer use. After looking at really collaborating within the sector, there's also, as I showed in the previous slide, an element of partnering with downstream players in the value chain. So really looking into relationships and coalitions along the distribution chain. You only need one in each chain to then create this impact throughout. And there's also this element of commercial partnerships in the food system. So conscious of time, I think I'm currently at time, and I would like to conclude with what we've looked into today, right? So the current state of play, as Francesco also highlighted, mineral fertilizers are a huge element of the total emissions. So about 2% of total emissions comes from fertilizer. The need for collaboration is really critical. So looking at your scope 1, your scope 2, and your scope 3, so 50 to 80% of emissions actually come from fertilizer use. It's not only this focus on production. Thirdly, we looked at the key interventions, looking at the impact of NUE improvements, inhibitors, and the wider food systems change. And that then really translated into the actions you can take. So really looking first at the individual actions you can take. Secondly, collaborating with others in the sector to create this movement. And thirdly, the importance of partnering with downstream players through the value chain. So thanks very much. And then I would like to hand over back to move to the next presentation.
Thank you very much, Flor, and a great presentation. Yes, that's what I wanted to refer to. So, so the majority of the participants before your presentation, so that we can reduce N2O emissions between 1/3 and 2/3. So now I hope that many of them are convinced that we can reduce them by at least 2/3.
Let's hope so.
Yes. So now I would like to remind the speakers, especially those who have done already their presentations, to look at the slide of questions. There are already more than 10 questions. So if you could respond already in writing to some of them. So with this, let me now welcome our next speaker. That's Frank Brentrup. So Frank is R&D, yes. He's R&D lead for sustainability and strategic research at Yara's Research Center in Hanninghof, Germany. Frank leads a team of scientists focusing on sustainability aspects of crop production and mineral fertilizers. He is Yara's representative in international organizations and initiatives such as the Cool Farm Alliance, Global Gap, and the European Nitrogen Expert Panel. So Frank is going to present on the role of the fertilizer industry to help farmers reduce N2 emissions and sequester carbon in their soils. And we will have a few Slido polls also during Frank's presentation. So over to you, Frank.
Thank you very much, Patrick. I hope you can see my screen and can hear me well. Does that work? I cannot see
yes.
anybody now, but I
Everything
assume
is
it works. Thank you. Okay, so let's go directly into the presentation. I would like to start with this picture or this illustration that really nicely shows that nitrogen management needs to balance between optimum crop nutrition for yield and quality on the one hand and protection of climate and nature on the other hand. And that's the challenge that we face. So we need the nitrogen fertilizer, as we heard in the beginning, to supply and provide enough food to address the yield and quality aspect. But at the same time, there's a challenge with excess nitrogen and nitrogen losses because they pollute water and air. They have a climate impact. That's why we need to look for a right balance and an optimum use of nitrogen use. And in this view or having this in mind and as a background, we see the following key actions to reduce the greenhouse gas emissions from crop production and in particular from fertilizer. So here it fits very well with the previous presentation from Flor, and I would also like to emphasize the importance of the nitrogen use efficiency increase to produce more crop with the same or even less nitrogen, to avoid direct N2O emissions, and of course all the other N losses from the soil as much as possible. We should not forget that increasing productivity on the existing land is important to avoid further land use change. There is some improvement that we have seen previously, but that's still a challenge. And then, of course, last but not least, we need to protect the soil carbon and support even more carbon sequestration through regenerative agricultural practices. I will focus on the first two parts here, and we'll start with the nitrogen use efficiency. So nitrogen use efficiency is really key. And what does it mean? It's the ratio of the nitrogen that we remove with harvested crops and the nitrogen that we input to the system, basically. Whether this is on a farm scale, on a field scale, or even on a country scale, can be applied at different scales. So the indicator that can be calculated from an input and an output is NUE expressed in percentage, an output divided by an input. So the value means the more an input is removed with a harvested crop, the better it is for the farmer and the environment. But it's a little bit more complicated if we look into the, say, calculation in more detail. So here you can see a graph showing the N input on the x-axis and the N output on the y-axis, and two lines of NUE values. The blue one is the 70% NUE value. That means 70% of the input is removed with a harvest as in grain or whatever is harvested from the system. And the 90% is the orange line, the upper line. So what we have concluded in the work of the nitrogen expert panel is that there is, of course, a limit in terms of high NUE. That means if we continuously in a system remove more than 100 or even 90% of the nitrogen, or let's say if we input less than 90% of the nitrogen that is removed, then we have a risk of decreasing soil fertility and soil mining. On the other hand, if we remove less than 70% of the N input, this means that 30% is lost to somewhere, is remaining somewhere. It's prone to, say, greenhouse gas emissions, ammonia emissions, nitrate leaching, and so on. So it has a potential impact, negative impact on the environment. That leaves us with a kind of target nitrogen use efficiency corridor, and we should aim on average on a nitrogen use efficiency of around 70%, but this is of course very context specific. It depends on the crop, it depends on the farming system, if it includes organic materials, if it's a livestock system, it's more difficult to achieve high NUE values because the organic nitrogen is more difficult to manage compared to mineral nitrogen. Just two examples what we can do to increase the nitrogen use efficiency, and it's important to understand that nitrogen use efficiency itself is not a measure, so it's just an indicator. It's the consequence of nitrogen management. So we need to change the management to improve the nitrogen use efficiency. And one important aspect is a balanced nutrition when we look from a fertilizer perspective, which means that only if all the required essential plant nutrients are available for a crop, it can take up and use the nitrogen efficiently. And here we can see the result of a long-term trial that we are still running here at our own research facility in northwestern of Germany. It's a rotation of rye potatoes and maize, and the data shown here are the average of the last 8 years. And it's showing 4 different treatments, one that received only nitrogen and no other nutrients, one that receives N and P, phosphorus and nitrogen, then nitrogen and potassium, and the full package of the required nutrients in this rotation. And it's only possible to reach the target corridor of NUE with a full balanced supply of nutrients in the long term. And that just shows that balanced nutrition, whether it's with mineral or with organic fertilizer or in a mix of both, is important for a high nitrogen use efficiency. Another example, and that was already mentioned, is precision farming. In this case, we use remote sensing combined with the crop nutrition plan to allow the use of a biomass mapping converted into a fertilizer application map. So on the left-hand side, you see the sensor result, biomass mapping of a field, and you can see different amounts of biomass on different parts of the field. And this has then been converted with an algorithm based on the end sensor work that we are doing in Yara into an application map, which allows the farmer to apply targeted amounts of nitrogen at different parts of the field. And what does it mean in terms of nitrogen use efficiency? You can see here, first of all, this is the result of the average of 16 field trials with oilseed rape at the eastern part of Germany. And on the left-hand side, you see the yield comparing a uniform application of the farmer decided N rate. And the blue bar is the end sensor fertilized part of the field. So there's a 4% yield increase. And at the same time, the variable rate spreading used 6% less nitrogen compared to the, let's say, common farmer practice. This results in an increase in nitrogen use efficiency, and the increase is from 81 to 89%, showing that already the farmer practice is very professional, very efficient, but it can be even improved with a precision farming technology. What does it mean for greenhouse gas emissions? So here we have used a larger sample of carbon footprint assessments in malting barley fields in Denmark and Finland that we have done with a Cool Farm tool as a calculator. So it's a full carbon footprint, including all emissions up to the farm gate. That means also emissions from machinery, from other inputs, from whatever is required to produce the malting barley. And we have plotted that against the nitrogen use efficiency at the same farm. And you can see that there is a clear relationship. It's not one-to-one, of course, because there are other factors that influence the carbon footprint, but the end use efficiency is clearly a key factor for the full carbon footprint per ton of grain, in this case, malting barley. So it's important to improve nitrogen use efficiency to reduce the emissions, the total emissions. But even at a, let's say, optimum nitrogen use efficiency, you still have N2O emissions because you still apply nitrogen, and this nitrogen is still prone to the, or it's part of the conversion processes in the soil. And we have, various sources of direct N2O emissions from nitrogen. It's not only the mineral fertilizer, the mineral nitrogen fertilizer that leads to emissions. It's also the decay of crop residues, so the release of nitrogen from the mineralization processes. It's the cultivation of organic soils, which also includes the conversion of organic nitrogen, its application of manure, grazing animals, and of course N2O from indirect emissions. That means ammonia losses, nitrate losses that lead to N2O losses outside the field where the nitrogen has been applied. How is now nitrogen or N2O emission, how does it evolve, and what is the source of the emissions? There are two microbial natural processes in the soil. One is the nitrification, that's the conversion of ammonium into nitrate by certain bacteria, and that leads to a constant but small source of N2O emissions from soil. And then the main source usually is the denitrification process under certain conditions. If oxygen is depleted or limited in the soil, for example, due to a high water-filled pore space, then there is a relatively large group of soil microbes that can use nitrate instead of oxygen for the respiration. So it's a kind of survival mode under these extreme conditions. And on average, the IPCC assumes that roughly 1% of the applied nitrogen, whether it's organic or mineral, is emitted as N2O nitrogen. However, we know from research and science that the more dry conditions show lower emissions, while wet conditions with more denitrification and more denitrification events lead to higher emissions. So the new IPCC guidelines suggest a 0.5% emission factor for dry conditions and a 1.6 emission factor for the wet conditions. That means now we have to tailor the nitrogen management, for example, in terms of nitrogen form and timing to local conditions. And just to give some background or some evidence for these different emission factors, on the left-hand side, you can see a result from an experiment where under different water-filled pore space, which shows the, let's say, the wetness of a soil, ranging from 20% to 70%, how the N2O emissions differ depending on the moisture content of the soil. It's rather low, up to the 60%, and it's mainly driven by the nitrification process. And if in this experiment, and that has been shown in several other case studies as well, if the moisture exceeds a certain threshold, 60% or more of water-filled pore space, then the denitrification becomes dominant and leads to high emission peaks. And that can be shown here. And on the right-hand side, you can see modeled N2O emissions, annual N2O emissions in Europe. And here we can also clearly see that high emissions occur mainly in regions that also receive more rainfall, that have more moisture, more wet conditions than, for example, in Spain or in Italy, if you compare this to Ireland or the western part of the UK, for instance. So based on this knowledge, we can also manage and try to guide, let's say, farmers towards more climate-friendly nitrogen strategies. So one strategy is definitely to avoid application at times with a high risk for denitrification, wet conditions, accompanied especially with high organic carbon inputs, but also selecting the right product depending on the crop moisture and soil conditions. And here I would like to share with you one decision tree developed by Wageningen University, Feldhoff and colleagues, where they have distinguished between different crop types, grassland, arable, between conditions, the dry, moderate, and wet conditions, and then also based on the soil types, developed some recommendation in terms of nitrogen forms. So it's depending on the conditions, whether it's the ammonium nitrate based products that are recommended, or the ammonium based, urea based, and also including the nitrification inhibitor that can help to minimize emissions, especially under these under the conditions with high denitrification risks. Last but not least, I would like to share 2 slides on the last point, on the soil carbon and soil sequestration part. And here it's first of all important to avoid any land use change as much as possible. So to save carbon in the soil, of course, it's important to limit the conversion of, or avoid the conversion of, natural land with high carbon stocks to agricultural land, particularly arable land that has low carbon stocks. And then, of course, also certain management practices are important to support or to reduce the decomposition of the existing soil carbon. So reducing tillage intensity, reducing erosion, or the management of peatland is important to reduce to maintain high soil carbon contents in the soil. Sequestration is also possible, so increasing crop yields and residue amounts by improved crop nutrition, retain the harvested residues in the field, introduce cover crops to introduce extra biomass to the soil and get to a new equilibrium in soil carbon is a measure. And then, of course, recycling of organic matter that is produced elsewhere, so the addition of organic fertilizer, the amendments such as compost. But we need to be aware that the main amount, the bulk of the organic matter available for soil application is already being used on the farms, and it doesn't really help just to redistribute this. It's important to, let's say, use the currently not used amounts of organic matter and to increase the recycling of that organic matter, rather than just moving organic matter from one farm to the other to achieve some let's say local improvements on the expense of other regions. To summarize this part of the of the talk, increasing nitrogen use efficiency is important and can be achieved by best nutrient management according to the 4 R's. Avoiding direct N2O emissions. Here, the focus should be on the right nitrogen source under specific conditions, of course, including also the use of inhibitors. Increasing productivity on existing farmland. This is very well summarized under the heading of sustainable intensification. And then protect soil carbon and support carbon sequestration. That's the main topic of Regen Ag that we also support. And with this, I hope that I was within the expected time frame, so that we have some time for David to present as well.
A bit over time,
thank you
but
very much.
thank you very much, Frank. And so let's not invite the last speaker in the interest of time. So that's David Cantor. David is Associate Professor of Environmental Studies at the New York University, and he is also chair of the International Nitrogen Initiative. So his research examines new policy options for addressing nutrient pollution and how to manage a transition to a global agri-food system consistent with the Sustainable Development Goals. So over to you, David.
Thank you very much, Patrick. Just putting this into
Yes,
screen.
full screen, perfect.
So I'll be succinct. and focus on some big questions and ideas to get our brain juices are flowing and just continue to boil them. So the central points that I just want to cover in my brief talk right now is this idea of halving nitrogen waste has become a major global and national ambition. And when we talk about halving nitrogen waste, and I'm sure many of you have heard about this before, it's another way, at least in my mind, of talking about halving nitrogen losses or halving nitrogen pollution, all the nitrogen that goes into the Earth system that does not end up in its intended end product or end use and then is lost to the environment. The challenge now is how we actually operationalize this target. It's good that we have such an ambitious target and that it has been included in many regional and global venues, but the challenge now is how do we actually make it a reality? And the current policies that we have on the books, a lot of them are not equipped to implement such an ambitious target. And in previous analyses of nitrogen policies around the world, they tend to be more weighted towards food production. When I say they, I mean nitrogen policies tend to be weighted towards food production rather than environmental protection. And so we need to consider more creative and potentially transformative actions and policy. So just to give a bit of a timeline of the halving nitrogen waste, it's all been very recent. There was the first UNEA resolution in 2019. The UNEA is the UN Environment Assembly, which is the UN's main environmental decision-making body. And they had the first sustainable nitrogen management resolution back in 2019, highlighting it as a problem and requesting a process for better nitrogen management. But the first time that this idea of halving nitrogen waste made it into a policy document was the Colombo Declaration, which was just over 4 years ago in Sri Lanka, and about I believe 30 countries or so have signed on to the Colombo Declaration, including Brazil, Germany, and Pakistan, which includes this ambition to halve nitrogen waste by 2030. That then made its way into the EU Farm to Fork strategy, where it's one of the 4 pillars of the EU's Farm to Fork strategy, and that includes nutrients, so both nitrogen and phosphorus, and the halve nutrient waste goal is supplemented by then this goal of wanting to reduce synthetic fertilizer application rates synthetic fertilizer application use by 20% by 2030. It was then, there was in the follow-up UNEA resolution in 2022, last year, there was a goal of significantly reducing nitrogen losses, and the halve nitrogen waste didn't quite make it in there, but then it did make it in to the post-2020 UN Global Biodiversity Framework, this Kunming-Montreal Global Biodiversity Framework, where Target 7 includes an explicit goal of reducing nutrient losses by at least 50% by 2030. And not wanting to toot the horn of either NYU or the scientific community, but actually where this goal of halving nitrogen waste came from was just 3 floors above me in New York, in a dingy beige conference room in 2018, where we were having this discussion around nitrogen scenarios. And we also were asking ourselves, what would the equivalent of a 2 degree or 1.5 degree kind of target be for nitrogen? And that's where, at least I believe, these first discussions around this idea of halving nitrogen waste came out. So now the challenge is, how do we translate these targets into action? We had a workshop in Paris last year on this topic, right? And the main kind of vehicle for implementing these targets is this idea of national action plans. In many ways, there's a big similarity to the Paris Climate Agreement, where this idea of you have an overarching target, but the way it's implemented is each country comes forward with their own national action plan for how it should be done. And so we kind of outlined the steps for how we believe these national action plans should be developed. First is having and some of these steps may seem obvious, but I think it's important to have a standardized approach. And for many countries who haven't yet really considered the nitrogen pollution problem, I think it's important to have this guidance out there. For many, nitrogen pollution is obviously spread across many ministries and sectors and agencies. And so identifying a working group within a government is very important, engaging a broad spectrum of stakeholders. Having an initial nitrogen assessment for a country, understanding what your baseline is. And then we had a lot of discussion around what kind of given the different national scientific and financial capacities, the different tiers of complexity, kind of like the IPCC does for estimating emissions. You have tier 1, which is more the emission factors, kind of IPCC emission factors, all the way to tier 3 of national biogeochemical modeling. And then in terms of the national action plans themselves, and I'm happy to share with you this guidance document we put out, but we go into detail on what kind of the development of concrete targets, focusing on concrete targets and sectors looks like, designing new or amending existing policies, and being clear in terms of the plans for implementation, monitoring, and reporting. Now, as I said, the problem is that current nitrogen policies prioritize food security over environmental protection. This is from a paper we came out with a few years ago, with the pie chart on the left is all the policies around the world that we identified, kind of broken down by sector. There's another set of policies that are organized by impact, environmental impact. But the ones organized by sector, when you just look at the left pie chart, you think, okay, well, this actually reflects the work that, if you look from Francesco's presentation, right, where most N2O, for example, comes from agriculture, then this is just the number of policies, but they tend to reflect the distribution of pollution. But when you actually break it down in terms of types of policies, if you look at the type here in terms of commerce, and then pro-N, those are commercial policies are ones that either facilitate the trade or standardize the use of fertilizers, and pro-nitrogen policies are ones that subsidize fertilizer use. And so and then the economic and regulatory tags are the only ones that put quantifiable constraints on nitrogen pollution. And so it's clear that there's this imbalance towards policies that incentivize food production, which again makes sense. Nitrogen is this essential resource. But just to understand that balance in the current policy landscape, we're definitely skewed towards using nitrogen for food production and not more sustainable nitrogen management. And even when we have tried to make nitrogen management more sustainable, we've run into resistance. These are just some photos from the Netherlands on the left, France on the top right, and actually this Canada in the center there. They have Dutch flags in solidarity with the Dutch farmers protesting. But there have been some of the biggest protests that we've seen, whether it be the longest traffic jams in the Netherlands, or the most mobilization of these rural communities in response to efforts to reform, to try and take these policies and make them more stringent in line with these global targets. Now, a big part of my own personal research is based on this premise that a lot of policies focusing singularly on farmers and how we can get them to change their behavior are in many ways misguided, because it projects or assumes a lot of agency on the part of farmers, or more agency than they actually have. And one of the significant insights from, say, the rural sociology literature is that actually farmers are very constrained in the choices that they have. They're constrained by regulatory constraints, economic, social, informational, structural constraints. And by that, I mean everything from where they get their information, the kind of production contracts that they're under, the size of their farm, their network, and obviously the demographics of the age and education level. So these constraints beyond the farm that ultimately influence what happens on the farm, right? And so that idea that these constraints are coming from actors and institutions beyond the farm lead to then the conclusion for me, that we need to address these constraints beyond the farm and expand our idea of what nutrient pollution policy and governance looks like. This is just one slide from a report we did at the law school at Sciences Po, where we were looking at, in Brittany specifically, because there's a big green algae problem there, looking at policy interventions beyond the farm that could ultimately influence what happens on the farm. Everything from tackling the incentives that farm advisors have and how they advise farmers, or using animal welfare laws as a leverage point to try and address nutrient pollution. But ways to look beyond the farm, instead of just targeting farmers and their behavior, considering the forces and institutions beyond the farm that ultimately lead to the conditions in which farmers are applying what they're applying and why. Some of these points have been made before in terms of, but I do want to just emphasize this, that, this emphasis on fertilizer use efficiency and the 4 Rs is very much operating within the same system that we're currently in. And that makes sense. We have this highly industrialized and highly specialized food system. But, you know, we should also, and this is both a call to the policy community and the scientific community, I think be more creative and a bit more ambitious in how we think about the kind of policies that we want. And this was clear in Flora's talk as well. But whether it be a shift in diets or lowering regulatory barriers for alternative forms of meat production or integrating crop and livestock production more clearly, there are, I think, ways to be a bit more creative. I've just got a couple more slides. And again, just to be a bit provocative here, you know, the 4 Rs are a very useful tool, and I totally agree that if they were fully implemented, then we would make a lot of progress towards more sustainable nitrogen management. But that's a big if, and at least in my mind, that's where the role of policy comes in, and also where perhaps these 4 Rs might be supplemented by what I've called, and apologies, the 4 Ts, where we transform nutrient management beyond kind of the traditional tools, and go towards some of these more, push more innovation in a way that that again, Flora and Frank were talking about. Transform how we manage nitrogen off the farm, whether it be everything from food waste to, again, these alternative forms of meat production. Transform how we govern nitrogen in these more creative ways, and also transition and transform in a way that respects different national pathways and growing cultures across generations. So that's hopefully just, again, some ideas I wanted to splash out there. Happy to take questions and to hear from the other panelists. So thank you very much.
Thank you very much, David. That was a very good summary of what are the, let's say, possible policy interventions to improve management of the nitrogen cycle in agriculture. So we are behind schedule, but let's say, to give justice to the possibility to have Q&A, I suggest that we take another 15 minutes. So now, and I will hand over to Stephanie to moderate the panel discussion. So Stephanie van der Poel. So Stephanie has a background on political science and environmental management, and works as a program management officer at the Source to Sea unit, focusing on nutrient pollution at the United Nations Environment Program, UNEP. And UNEP provides also the secretariat to the Global Partnership on Nutrient Management, GPNM, a global multi-stakeholder partnership addressing the nutrient challenge. And by the way, both FAO and IFA are a member of the steering committee of GPNM. So with this, Stephanie, over to you, and let's take 15 minutes to have a good discussion with the 4 speakers, and also to respond to some questions of the audience. Over to you, Stephanie.
Thank you, Patrick. I'll try to be quick as well. There's quite a few questions on the Slido, and I encourage everyone to have a look because there's a very interesting set of questions there. But perhaps I'll address one to Floor. What is your view on the current problems with MBPT as a urease inhibitor and need to find alternatives? What are the most promising alternatives being researched?
Sorry, putting myself off mute. So there are lower tech alternatives already in use. So for example, neem coating of urea granules is mandatory in India currently. But currently I'm not aware, my colleague also not aware of kind of the higher tech alternatives to MBPTs. So we do know that it's an active area of research. So possibly David Cantor might know more about this. Happy to hear his thoughts.
David, if you want to complement to that, otherwise we could also reply on the Slido.
I don't, and would prefer to leave time for other questions.
Yeah, no problem. Okay, so question for Frank. It can be difficult to avoid applying N in wet conditions since crop yield response to applied N is usually larger. Would it not also be important to increase use of the existing inhibitors of nitrification and to do more research on yet more effective inhibitors? That was a question from Tom.
Can you repeat the first part of the question? I didn't really get the first half of the sentence.
it can be difficult to avoid applying N in wet conditions, since crop yield response to applied N is usually larger. Would it not also be important to increase use of the existing inhibitors of nitrification and to do more research on yet more effective inhibitors?
Yeah, of course. I mean, there are situations where nitrogen application to in wet conditions cannot be avoided. Yeah, definitely. And then under these conditions, for instance, if the extreme would be paddy rice, that's the wettest condition I can imagine, but also grasslands in certain regions, like we have seen in Ireland, are pretty wet. And there, of course, the nitrogen form is important, like nitrates under these conditions are not a good idea because they would lead to denitrification, while, for example, the use of urea under such conditions is pretty safe. So that's also why it is used in paddy rice, for example. And if required, like for urea, to make it more efficient, the urease inhibitor that has been mentioned before is helpful to reduce the ammonia emissions. And it can also be, let's say, beneficial to add a nitrification inhibitor, but research has shown that already the use of urea under that condition is pretty much reducing the N2O emissions. But wet is, I mean, it's a relative description of a situation. There's many conditions in between dry and wet, and that makes it more complicated.
Thank you, Frank. For Francesco, on the graph you were showing on the world total agri-food systems emissions 2021, synthetic fertilizers have a lower impact than manure. FAO has promoted organic fertilizers over synthetic fertilizers. Why?
Thank you, Stephanie. I also typed in an answer at some point in the back. Yeah, so actually, it's a function of how I aggregated the data, because the data there of emissions from manure, just following how countries report them, include emissions from so-called manure left on pasture, which is actually the larger amount, and what we call manure, which is actually collected, treated, and then applied to soil as an organic fertilizer. So it's actually that component which is much smaller, say 4/5 versus 1/5 of that total number that is on the graph for manure, that should in fact be compared to the synthetic fertilizer emissions. And in that case, it's actually smaller. I mean, that's an answer on the numbers. On the promotion, of course, there's more than just N2O emissions in nitrogen cycle and management of soils. In fact, on the pasture part, the larger component is tied to natural, recycling of nutrients, and it's been tied to soil carbon sequestration under the right management conditions. So, yeah, I hope that answers the question.
Thank you. Perhaps I could ask one more set of questions if time allows, Patrick. And some have been answered on the Slido, but also perhaps not everyone is reading these. Fleur, how can investors in and lenders to large global food companies incentivize the adoption of these interventions, or should government action regulations be prioritized? I know you've put an answer, but perhaps you would like to explain that just in case people haven't seen it. Thank you.
Definitely. And so I was at COP last week, and I think it's a never-ending question, right? So should we point to government, or should we act ourselves? And I think the answer is, of course, collaboration is key, and waiting for government action is not an excuse to also see what you can achieve yourself. So yeah, government can play quite a big role, but the impact of global food companies should really not be underestimated, especially as they can partner with retailers to actually reward farmers for making changes to their practices. And I think there was also a very good question in the chat highlighting the large impact of farmers, and not necessarily that now out of the 160 people or 90 people, there are not a lot of farmers currently participating. think that's quite critical. And how do you reach these farmers? I think that is through these large food retailers and kind of throughout this value chain. I hope that answers somewhat the question. I'm happy to hear others kind of challenge that element.
Thank you, Floor. A question for Frank. Since nitrification plays an important role in N2O emissions, what would be the impact of nitrification inhibitors, thinking about your decision tree that you had on your slides?
Yeah, the nitrification inhibitor is, let's say, delaying or slowing down the nitrification process. So if, well, it's different to the denitrification. Denitrification gives peaks of emissions. So if these peaks can be avoided, that's more efficient than slowing down the nitrification process, because it, of course, certain part of the nitrogen will be taken up as ammonium by crops if it's longer present as ammonium, but still, I would guess, and I think research is also showing that even if the nitrification is delayed, most of the ammonium will still be nitrified sooner or later, and that process is just delayed. So from my experience, the main positive effect is to avoid high nitrate concentrations in soil at times that have a risk for denitrification, and that's where the nitrification inhibitor is helping most. So the nitrification process is more kind of a background, constant release of small amounts of N2O. That can be best avoided by applying nitrate, let's say, because there's no nitrification required.
Thank you. David, you talked about transformative action. Could you explain further what policy incentives are needed to accelerate adoption and implementation? So this is looking at policy incentives for transformative action.
Yeah, so I mean that's a big question. You know, I think to kind of make it perhaps more tangible, there have been, well, so for example, when it comes to alternative meat products, whether they be plant-based meat products or lab-based meat products, I think having a clearer and more kind of less arduous regulatory process, while obviously still being thorough, is important to ensure their widespread use and adoption. And then there are various policy options out there to try and increase the recycling and use of manure and increase essentially the everything from trading systems to better transportation, facilitating the processing of manure as an input. And then obviously a bunch of policies and policy proposals out there around ways to incentivize and drive dietary change in a way that does not, that still obviously respects national cultures, respects meeting various sustainable development goals, but different countries have had different proposals around that, varying from changing dietary guidelines to some financial incentives.
Thank you. And perhaps while we have you here, you focus on halving nitrogen waste loss. However, not every country has a baseline. Why half? Why not more or less?
Well, you know, putting together a target is as much an art as it is a science. Now, that being said, when you look at the science, you know, it's clear, for example, everything from planetary boundaries to our ability to reduce nitrogen surpluses is in line with this idea that we can roughly cut in half the amount of nitrogen, either that is surplus or the amount of new nitrogen that we're putting into the Earth system to stay within boundaries. So that is in line with the scientific literature. But at the same time, kind of like the 1.5 or 2 degree target, you need something that is also that is catchy, that can make its way into policy discussions. If you know, a target that says, well, reduce it 60% here, 35% there, 76% over here, is not going to get as much traction. obviously. And now, to be clear, to me at least, you know, that target of halving nitrogen waste is really at the most granular scale, a regional target and really a global target. And so obviously the implementation of it is going to be very different in different places. Countries or regions that vastly overuse or over-apply nitrogen fertilizer can go way beyond the halving, right? And then there are going to be parts of the world that can actually increase the amount of nitrogen they're consuming because they're a very small part of the global nitrogen surplus, and the emphasis really needs to be on guaranteeing food security in those regions, or that they can do that and still not have much nitrogen losses at all, while hopefully avoiding the same development pathways that more developed countries did when they were developing their agricultural systems. So that's just a bit of insight into that.
Thank you. And one final question for Francesco. This, perhaps, I think this your background with IPCC. Can you comment on improved reporting and measurement from countries and allowances from IPCC directives? Fertilizer emissions is used only and not how applied.
Thank you for that. I think I've seen it
Or,
in the... No, that's okay. I mean, it's hard to reconstruct the entire meaning. Well, I mean, if we're looking at the way the countries are required to report their emissions, I suppose the answer is about, you know, do the guidelines do justice to the entire set of recommendations in good management that are linked to emissions? But I think indirectly that's captured by the way countries report. You know, of course, at the end of the day, you just attach a coefficient which is highly uncertain to an amount applied, rather than, like you're saying, the management type. So I mean, that's basically a discussion of reporting at different tiers, right? So if you're reporting at tier 1, you basically cut yourself short for, you know, getting rewarded, you know, by improving management, let's say, along, you know, more complex lines. So they do justice, I think, because they provide a playing level field where everybody can report something and participate to the political process. But I think once you include these possibilities of doing the higher tiers, you know, then it's a matter of being able to report that. And so the IPCC guidance, in fact, allow for that. Make it more difficult because you need more information, you know, the kind of information that Frank referred to, you know, more highly detailed data collection processes. But in principle, it's possible.
Great, thank you. Patrick, over to you. But first, thank you, IFA and FAO, for inviting us here today as well from the GPNM and UNEP side.
Well, thank you, Stephanie. Thank you, everybody. So we have had a very, let's say, informative and inspiring set of presentations today, and that was followed by also a stimulating discussion. And I hope that all of you have enjoyed it. So at a time when countries have just committed to reduce the use of fossil fuels, as I mentioned earlier, the fertilizer industry aims to decarbonize fertilizer production, especially ammonia production, which is the most energy-intensive part of our industry. But minimizing emissions from fertilizer use is equally, if not even more important, to remain aligned with the 1.5-degree objective of the Paris Agreement. And by reducing these emissions from fertilizer use is, however, much more complex than reducing emission from fertilizer production, because we are not dealing just with a few hundreds of fertilizer production plants here. We are talking about hundreds of million farmers, with many smallholder farmers who not always have access to information. On top of that, we need different solutions for different countries, different agroecologies, different farming systems. So that's really very complex. And so the key question is really how to reach out to this diversity of farmers and to incentivize them to change their practices and adopt best management practices and innovative solutions. And to do that, it really requires partnerships between all the stakeholders. And I am pleased really to see some progress in recent years in this field. Just for instance, at COP28, despite stalling negotiations on agriculture, we see public and private initiatives and partnerships shaping up, and they continue to advance. That's great. And it is because really these partnerships are so essential that we have organized this webinar today to make sure that everybody is aware of the issue and that we can work together, and we can and we should work together to fix the issue of especially N2O emissions from fertilizer use. So with this, a big thank you to our 4 speakers, so Francesco, Flor, Frank, and David, as well to Stephanie for moderating the panel discussion. Thank you as well to our, let's say, partner, FAO, and to the 200 plus, so we were more than 200 participants just during, let's say, the middle of the webinar today. If there are still some questions that have not been answered, so we will share them with the 4 presenters. And we look definitively forward to having you with us for future, let's say, webinars. And we wish you a nice rest of the day. Thank you very much.
Thank you all. Thank you, Patrick.
A big thank you, everybody.
Thank you very much.